In this video, I'll explain the difference between energy and power. I'm going to go back to this example. You've seen it several times in the first video. It's the one where if we lift the 1,000 kilogram beam and we do it to a height of 15 meters, that required a work of 150,000 joules. You could also think of it as we change the potential energy of the system by 150,000 joules. We're going to add a new dimension to this problem, time. So let's say it took 5 seconds to lift the beam to this height. How much power was required to do this? Well, that brings up the question, what is power? If you grew up when I did, this is power. If you don't know who this guy is, then you missed a wonderful part of childhood. We can define power as the amount of energy done per time it takes to do that work. Let's define power as the amount of work done per time it takes to do that work. Per here, that's just a fancy way of saying divide. So our definition of power is really work done divided by the time interval, or the time it took to do that work. In video 1, I explained that work is just a change in energy. So power could also be defined as a change in energy divided by the time to make that change. So now we're ready to answer this question. So we know the work, and let's say it took 5 seconds to do that work. So power would just be the work divided by the time, which gives us 30,000 joules per second. Now this unit, joules per second, is something special. We see it a lot. 1 joule per second is 1 watt. So we use a symbol of a capital W for watt. So we could say then that this required 30,000 watts of power. That's actually quite a bit. And I should mention that this is actually the minimum amount of power that we would need. In next video, we'll talk about efficiency and how that could change this, but at minimum, we would need a power of 30,000 watts. To give you some comparison for what that amount means, a high-powered microwave will use about 1,000 watts. So lifting the beam just 15 meters in the air in 5 seconds is like running at minimum 30 high-powered microwaves. You can see how if you're doing this all day, it would require a lot of energy consumption, and it's going to be expensive to run this giant crane. Well, what if we're in a hurry and 5 seconds is just too slow? So we cut the time in half and we lift it in 2.5 seconds, the same height. How would that affect the power? Well, let's just plug the numbers into our definition of power. That results in 60,000 watts, which is exactly twice what we had before. So we can say then that half the time requires twice the power. I also want to point out that we use the same amount of energy for this power calculation. It's because the beam was lifted to the same height either way, and that's where the energy or the work was represented. So it's an important observation to notice that half the time requires the same amount of energy. So you've heard the phrase time is money. Well, if money in this case you think of as energy, then you really haven't gained anything by saving time. So yes, you spend less time, but your rate of energy consumption increases so that you actually use the same either way. There's other examples of the same principle. For example, if you're driving in a car and you decide to go faster so that you arrive at your destination sooner, it's tempting to think that you've actually saved yourself gas because you're driving for less time. But in fact, you don't save yourself any. It's the same amount of energy no matter how fast you're going. So yes, you'll save yourself time, but you also spend that energy quicker, so you don't save yourself gas in that sense. In fact, you end up using more gas because the faster you drive, the more air resistance you'll encounter, and you also decrease the efficiency of your engine, running at higher speeds, higher temperatures. So in that situation, you're paying for that time you saved by spending extra gas money. Well, then let's consider the opposite situation. Let's say we have plenty of time to do this. So we lift the beam in 10 seconds. What's the power then? So that uses 15,000 watts, which is half of our original 30,000. So we can claim then that twice the time requires only half the power, but it's similar to last situation, we still use the same amount of energy either way. So hopefully this emphasizes the difference between power and energy. They're related, but they're certainly not the same quantities. Power includes the dimension of time. So I think you're ready for this question. It's kind of a long question, but I want you to read through it carefully. I'm going to give you several seconds to just read it rather than me explain it to you. Okay, I hope you've picked an option. If you haven't, read through it again and really try to commit to one that you think is correct. Okay, so the answer in this case is B. Both of you did equal work, but you had less power. The work in this problem is just the gravitational potential energy that you gave the suitcase. So that was the change in energy that you provided. The gravitational potential energy is defined as the mass of the object, so in this case, the 15 kilograms, the acceleration due to gravity, which is the 10 meters per second squared, and then the height that the object gained. And for you and your friend, you both walked up 2 flights of stairs, so you both gave it the same height and same mass, same acceleration. So long story short, you both did equal work. Power includes time, and since you took longer, twice as long, in fact, you used less power. Our next video will be the last one for Chapter 7. In that video, we'll go over machines and efficiency.